market prices. Let's look a little bit into the different technologies that can help us here. To start with, these receivers don't exist today in the market because none of the available technologies for itself is capable of meeting the requirements in all environments. So what do we need to do? We need an RTK solution, including correction data, to have an initial position accuracy in the centimeter level. We call this SSR RTK. You need then as many satellites as possible to have good signals and to have strong phase lock. This is multi-GNSS in its core. You need all the systems starting with GPS, Galileo, Beidou. You need all of them, and this gives you enough measurements to always take the measurements which are not affected by multipath, which are unobstructed, and which gives you a very high confidence. You need then a multiband reception, L1 and other bands like L2 or L5. Many people believe this is for accuracy. That's a misconception. The main benefit is not accuracy, but fast time to convergence. In other words, we use multiple bands in order to achieve this very, very high accuracy within seconds. A u-blox receiver with RTK capability today achieves the required accuracy on an L1 band, but it takes many, many minutes. This is unacceptable for the car use case. We have to have this in seconds. That's why we need multiband. And last but not least, we need 3D automotive reckoning. This helps us to smooth multipass effects, essentially work in areas where I have a lot of signal reflections. But it also helps us to navigate if the signals are lost for a short time, for instance a bridge or an underpath, we still need to coast through this. It helps us to recover the signals immediately afterwards and to have this very high accuracy within seconds again after we have passed through the bridge. And obviously we also need to maintain position in tunnels and parkings. That's also very important. Ultimately, what we have to do is we have to synergetically combine all those four technologies in one receiver. So the art is to combine existing technology very, very tightly. This gives us the required performance. This slide shows you results which we have achieved in a very early prototype. As you can see, it's easy to recognize the lane and the lane changes here. So the technology can achieve it. It's possible to have GPS with the required accuracy. And it's the combination of different technology which does it. Now let's look at the system view. How does this work? Well, the system consists of a safe GNSS receiver. That's obvious. So we have to have a receiver which meets all the criteria laid out before. But then we need a correction service and monitor all the GNSS satellites, calculate the corrections, and then we have to bring this corrections into the vehicle. This we do typically in two ways. One is through a satellite communication receiver or link, and the other one is typically through internet connectivity. And we see on this slide why this is needed. This shows you how a GNSS correction service works. You have a local reference system, so we need to measure the GPS satellites. We have to monitor them on a global basis to find out how accurate they are, but also to find out if a satellite fails. So we need a very dense network of GNSS reference stations. Now, out of this raw data, we have to calculate then the specific correction in a processing center, and we have to have this processing center with redundancy in multiple locations. Now, we have the corrections, but we have to bring these corrections into the vehicle. As mentioned before, there are two different transmission channels. One is satellite distribution. Satellite distribution has the main advantage that it comes through the very same antenna as the GNSS signals. And there are no transaction costs. If you have the satellite receiver, you receive it wherever this satellite distribution is visible, or the satellites are visible. So it's a very, very easy and compelling way of bringing this into the vehicle. The disadvantage is that if you are in an urban area with a high-rise building, make it so, for instance, you may not see this communication satellites. This is when internet distribution kicks in. Because in these areas you have perfect cellular networks, and you can distribute the correction through a cellular network or even other means like DNB into the vehicle. If you combine these two things, then you have a permanent link to the correction service. And this is exactly what you need. We need a constant stream of data into the vehicle. Now, let me talk a bit about the importance of integrity. Integrity is basically the trustworthiness of the system. I mentioned before, in a level 4 system, the driver is allowed to do non-driving tasks, be it some paperwork, be it email, be it sleeping. You don't want the driver to come into the loop within seconds, because that would be dangerous. He would make a lot of mistakes. But that means our system needs to be fail operational. And fail operational means the system remains operating even in case of a failure. So if one part of the system fails, another part of the system needs to take over. Essentially, this means that the total position function needs an ASIL D level. And because we use redundant positioning system, including GNSS, we can break down or decomposition these safety requirements to a level B or more, but a level B typically for the GNSS receiver. However, that's still something that is not yet on the market. So that's a very, very new requirement for a GNSS receiver. Going back to a level 3 system. Theoretically, a level 3 system would only allow very few non-driving tasks. the driver can be distracted for a few seconds, but whenever we have a failure in the system, the driver needs to back up. So you give an alert to the driver and the driver takes over. So the driver is the fallback system. That makes the system much, much easier. However, can we really count on the driver as a backup system? Well, I show you a relatively poor video from YouTube, which gives you a hint how much we can trust the drivers. Let me see if it plays. I'm sorry for the poor quality of the video, but the video really nicely shows the problem we have with drivers. What you see here is a Tesla self-driving, and the driver here is, do we see it? He's asleep. Maybe I used the mouse here. So this driver drives on a highway and he sleeps. There's in Teslas. A Tesla is not a level 4 system. So this is the reality which we have to deal with. People are not 100% trustworthy. Primarily about accuracy. It's about safety and it's about integrity, and we need to avoid these headlines if you want to make autonomous driving a success. However, if we need to guarantee the position accuracy, we need integrity, and very, very high integrity.